In the last video, we looked at the central limit theorem, and in this video we're going to use the results from the central limit theorem to calculate a confidence interval for a population mean. And so we're going to use this data here, and let's take a look at the data in a histogram. So this data is the eye span of, I think it's a particular type of fly. Is that what it is? Yeah, the stalk-eyed fly. And these are the distances, I guess, between this fly's eyes. And we don't have a very big sample here, so we could actually look at the entire data set. Why don't we do that? So let's make sure I spell it right, otherwise it's going to give me an error. Okay, so we've got a pretty small data set here. So this is the data, and what we want to do is come up with a confidence interval for the population mean, if we're thinking about this sample as coming from a larger population. So what we're going to do is, as I say, we're going to use the results of the central limit theorem. And remember, the central limit theorem that we reviewed in the last video says that if we take a sample from a non-normal population, we end up with a sampling distribution that the sampling distribution for the mean that is normal. And in particular, the mean of the sampling distribution is the population mean, and the standard deviation of the sampling distribution is the population standard deviation divided by the square root of the sample size. So that's all well and good, but it doesn't actually help us in this case, because this is the usual case that we face ourselves, that we face in statistics. We have a sample and we're trying to make an inference about the population. So we don't know what the population standard deviation is. So we're going to need to estimate it. And when we're in that situation of having to estimate the population standard deviation, because we don't know what it is, and we have to use our sample standard deviation as an estimate of the population standard deviation, then it turns out we don't have a normal distribution anymore for that sampling distribution of the mean. Instead, we have something called a t-distribution. And a t-distribution looks very similar to a normal distribution, so it still has that classic symmetric bell shape to it, but there's very subtle differences, particularly in the tails. The tails tend to be a little bit fatter. So there's a little bit more probability out in the tails than there is with a normal distribution. And then the other difference is that there's many different kinds of t-distribution, and the number that tells us the particular t-distribution that we're looking at is something called the degrees of freedom. And so this is an integer, and that tells us essentially how fat those tails are. That's one way of thinking about it. The smaller the degrees of freedom, the fatter the tails, and the higher the degrees of freedom, the more and more like a normal distribution the density curve looks. And so anytime we work with a t-distribution, we need to know for that particular context what the degrees of freedom is. And so you'll see that throughout this course we're going to use the t-distribution on many different occasions, and the degrees of freedom is always specific to the particular type of analysis that we're doing, the particular technique we're using. And so there is not one universal formula for the degrees of freedom. It depends on the particular technique. So in this case, when we're calculating a confidence interval for the mean, the formula for the degrees of freedom is the sample size minus 1. So that's the degrees of freedom for the t-distribution in this context. Okay, so I think we have all the information we need now. We just need to put everything together. So a confidence interval always has a similar format. There's always the middle of the interval, which is the point estimate of the population parameter we are estimating. So in this case, the sample mean is going to be that point estimate. So that's going to be our middle value in our interval. And then we add on or subtract a margin of error. And that margin of error in this case is equal to a percentile from a t-distribution with n-1 degrees of freedom times the standard error of the mean. And the formula for the standard error of the mean is the sample standard deviation divided by the square root of the sample size. Okay, so let's put all that together. And what we're going to do is we're going to use some language here that will be consistent every time we do a confidence interval. So I'm going to call alpha the significance level. Okay, and we've used that notation or terminology before when we looked at hypothesis tests, and we're going to use the same idea with confidence intervals. So a 0.05 significance level is equivalent to a 0.95 or 95% confidence level. Okay, so if alpha is 0.05, then 1 minus alpha is 0.95, and that's our confidence level. Okay, we'll next calculate our sample statistics. So the sample mean and the sample standard deviation. We're going to figure out the sample size. So that's 9 in this case. There's 9 numbers here. Yeah, I'll just show you. So n is 9. And then we'll calculate the standard error. So the formula is sample standard deviation divided by the square root of the sample size. So we'll calculate that. You'll notice the way I'm doing this is I'm making calculations, but I'm creating new objects in R with the names of what I'm calculating. And the reason I'm doing that is because I want to be as accurate as I can, and I don't want to lose any accuracy in my calculations when I'm multiplying numbers together and adding them together and so on. So I'm not going to work with the numbers directly. I'm going to work with these objects I'm creating, and that way R will store these numbers here to a very high degree of accuracy, and I won't have to worry about making any rounding errors. Okay, so this is a very good habit to get into when you are doing calculations in R, is to name things and then use the names of the things you're calculating, and that way you won't lose any accuracy in your calculations. If you want to look at the value, you can just enter the object and you can see what the value is. Okay, so there's no downside to doing this, there's only upside. Next we'll calculate the degrees of freedom, and then the next piece that we calculate is what's called the critical value. And the critical value, it might look like a fearsome piece of code here, but if I look up what this function is, okay, remember you can always do this anytime you see some code and you don't know what it is, you can always look it up and find out what it is. So it tells us that this is the quantile function for what's called the student t-distribution. Student was the pseudonym of the researcher that developed this distribution. And then these are the arguments, and if you don't know what the arguments are, you can look here for the details, and then if you're still really stuck, you can read all about it, and if you're still stuck, there's usually code at the end to help you figure out what to do. Okay, but for us, this first argument, if we look back here, is what is called P here. So it's the vector of probabilities. In this case, we're just finding out the value for one number. And so it looks like, actually let's see what that comes to. So 0.975. So what's going on here? Why, if I said my confidence level is 0.95, am I all of a sudden working with 0.975? So the reason is because with a confidence interval, you could think of the confidence interval, so in this case we're doing a 95% confidence interval. You could think of the confidence interval as having 95% of the probability in between the endpoints of the interval and 5% outside of the interval. And in particular, there'll be 2.5% outside lower than the left-hand side of the interval, and 2.5% on the right-hand side higher than the upper bound of the interval. Okay, so visualize that. 2.5% in the left tail, 95% in the middle, and 2.5% in the upper tail. And so the percentile from the t-distribution that I need, percentiles are defined so that they have a proportion of the probability on the left of that percentile, and then whatever's left on the right. Okay, so if I'm saying that I've got 2.5% to the right of the upper bound of the confidence interval, I have 97.5% to the left of the upper bound. And so that's what this number is here, the 97.5% or 0.975. So that's why you have to have, when you're figuring out your critical value, you don't have 1 minus alpha here, you have 1 minus alpha over 2. Okay, so that number, if we want to see what it is, it's 2.306. And then I calculate my lower bound and my upper bound. Okay, so in this case, the lower bound is, 8.47, and the upper bound is 9.08. So we're 95% confident that the population mean is between 8.47 and 9.08. That's how we would interpret this. If you want a more formal interpretation, you have to think about repeated sampling, and each time, hypothetically, if you were to take repeated samples from this population, so this is hypothetical because we can't do this in reality, but hypothetically, if we were to do this and calculate 95% confidence intervals for each of those repeated hypothetical samples, then in 95% of those intervals, 95% of them would contain the population mean, and 5% of them wouldn't on average. And so that's the technical definition, but much better just to keep things simple and just say we're 95% confident the population mean is in this interval. Okay, don't go using the word probability when you're talking about confidence intervals, because inevitably you'll end up making a statement that's not technically correct. And my advice is never use the word probability when you're interpreting a confidence interval. Say confident. We're 95% confident the population mean is in the interval. Okay, so that was a lot of work. It's actually much easier to use this inbuilt function, t.test. We could see what that function does. So this tells you all about what this function does. You might think, oh, well, this is doing a hypothesis test, which is true, but it also, if you look at the value list of values here, in the R help under value, it tells you what the output is for that function. And so there's one piece of the output which is going to give us what we want, confidence interval for the mean. And so that's why this piece of code is on the end here. This is going to pick out that piece of the output. I'm not interested in all this other stuff. I'm just interested in the confidence interval for now. We'll actually use this function later on when we do a hypothesis test for the mean, but for now this gives me the lower bound and upper bound of the interval that we calculated by hand here. So you might be asking yourself, well, why go through all of this tedious coding if I can just use one line of code? Well, in practice, sure, use one line of code. But the reason I went through all this was because when you're learning about confidence intervals, it's a good way to learn exactly what the calculation is doing. And I find it sticks better, and there's a deeper level of understanding if you can see where numbers come from, and you're not just entering some code and reading some numbers off, and you've no idea where they come from. Okay, so as practice, I invite you to do the calculation for a 99% confidence interval. We can confirm it using the t.test function. And so this is a good way of checking your understanding of how to calculate a confidence interval for a population mean.